Long before anyone dreamed of arranging the elements into a grand order, people had already begun pulling the building blocks of matter from the earth. Ancient civilizations mined gold and copper, forged iron into tools, and prized silver for its shine. These were the first elements they knew, each with its own stubborn character that refused to turn into anything else. Centuries passed, and alchemists chased new substances in smoky laboratories. They isolated sulfur from volcanic rocks and extracted phosphorus from urine. By the late 1700s, the French chemist Antoine Lavoisier compiled a list of 33 substances he believed could not be broken down further. His catalogue included familiar metals alongside newly recognized gases such as oxygen and hydrogen, yet the list remained a jumble, with no clear pattern linking one entry to the next. In the early 19th century, John Dalton proposed that each element consisted of unique, indivisible atoms. His idea gave scientists a way to weigh the elements and compare them. Soon more elements appeared, discovered through careful experiments with electricity and acids. As the count climbed past 50, chemists noticed repeating behaviors. Certain elements reacted alike when combined with oxygen or chlorine. Johann Wolfgang Dobereiner grouped some into triads, where the middle element's weight averaged the other two. John Newlands arranged all known elements by rising atomic weight, and observed that every eighth element shared similar traits, like notes on a musical scale. These patterns hinted at a deeper order, but the attempts still left gaps and awkward mismatches. Dmitri Mendeleev took the decisive step in 1869. He wrote each element's name and atomic weight on cards, then sorted them according to both weight and chemical behavior. When he reached a place where no known element fit, he left a blank space and predicted the properties of the missing piece. The table revealed families that stretched across rows and columns, turning isolated facts into a coherent system. Mendeleev's careful sorting had already hinted at deeper patterns hidden inside each element. Those patterns become clear once the table is viewed as a grid of rows and periods and columns called groups. Each row or period begins with an element whose atoms hold one more proton than the element before it. That count of protons is the atomic number, and it rises steadily from left to right across the row. As the atomic number climbs, electrons fill successive outer shells. The first period contains only hydrogen and helium because their single shell holds at most 2 electrons. The second period adds 8 more elements, while the second shell fills. By the time the table reaches period 6 or 7, the outer shells are larger and more complex. Yet the principle stays the same. Each new period simply marks the start of another shell. The columns, or groups, reveal a different kind of order. Elements stacked in the same group share the same number of electrons in their outermost shell. Those valence electrons decide how an atom will bond with others. That is why sodium in group 1 reacts violently with water, while potassium directly below it does the same, only more vigorously. Chlorine in group 17 readily gains an electron to complete its shell, and iodine in the same column behaves in a similar way, though its larger size makes the reaction milder. The repeating cycle of shell filling therefore explains both the length of each period and the family likeness within each group. Elements on the far left tend to lose electrons easily, while those on the far right tend to gain them. In the middle, transition metals show more varied behavior because their inner shells are still filling. Yet the overall layout keeps these trends visible at a glance. When an element is missing, its place in the grid predicts the size of its atoms, the charge of its ions, and even the temperature at which it melts. Modern measurements of atomic spectra and X-ray diffraction have confirmed those early predictions time and again. The structure Mendeleev glimpsed in 1869 now rests on the firm foundation of electron shells and atomic numbers, turning the table into a map of chemical behavior rather than a simple list. This map reveals clear trends that stretch across every row and every column. Atomic size shrinks steadily as you move from left to right along a period, because each added proton pulls the outer electrons closer. Drop down a group, and the opposite happens. Extra shells of electrons push outward, making atoms larger and their outer electrons easier to lose. Reactivity follows the same logic. Alkali metals on the far left give up electrons with almost no urging, which is why sodium flares in water and lithium powers compact batteries. Halogens on the right grab electrons just as eagerly, forming stable compounds used in everything from disinfectants to refrigerants. These patterns shape the materials that surround us every day. Silicon sits in the middle of the table where its moderate size and 4 valence electrons let it form the precise crystal lattices inside computer chips and solar panels. Engineers tune those properties by adding small amounts of neighboring elements, like phosphorus or boron, creating the semiconductors that run phones, satellites, and medical sensors. Further along the same row, transition metals supply strength and color. Titanium keeps airplanes light yet tough because its atoms pack tightly and resist corrosion. Gold and copper owe their conductivity and luster to the way their electron shells allow free movement of charge. In physics laboratories, the same trends guide the search for new states of matter. Researchers stack layers of elements with carefully matched sizes to build superconductors that carry current without resistance at ever higher temperatures. The periodic table even predicts which combinations might one day replace rare earth magnets in wind turbines and electric cars. Understanding these regularities turns raw elements into designed substances. A battery chemist chooses lithium because its small size and high reactivity store energy densely. A materials physicist selects gallium arsenide for light-emitting diodes because its band gap, set by atomic spacing, produces the exact color needed for efficient displays. Each choice rests on the same underlying order that Mendeleev first noticed, now measured and refined for technologies that power modern life